Hello viewers, this is the second part of my video on green chemistry. In this video, I am going to discuss about the principles of green chemistry. Here I am going to discuss the first and the second principle of green chemistry. Now let us begin with the first principle of green chemistry. This principle is about prevention of waste or byproducts. This principle states it is better to prevent the formation of waste rather than to clean it up after it is formed. Because the waste, if it is discharged into the atmosphere, sea, or land, it not only causes pollution but also requires expenditure for cleaning it up. The separation, treatment, and disposal of the hazardous substances is required, and this adds to the overall production cost of a synthesis. So it is better to prevent the waste rather than treat it up after it is formed. Now let us see one example. Here I have shown you the synthesis of ethylene oxide. This is the traditional method of preparation of ethylene oxide, and in this method you can see it is a two-step process. HCl, calcium chloride and water are produced as waste or byproduct. So in this method waste is generated. Now let us see another method of preparation of ethylene oxide. In this method ethylene oxide is prepared using ethylene and oxygen, and here only oxygen is the byproduct. So the second method is considered as a green method according to the first principle of green chemistry, which states it is better to prevent the waste rather than to treat it up after it is formed. So here with this example, the first principle of green chemistry is clear. Now let us see another example where we can see if waste is generated in a chemical synthesis, the waste can cause problems. Here I have taken the example of Leblanc process. The Leblanc process is to synthesize sodium carbonate from sodium chloride. And in this reaction, sodium carbonate, calcium sulfide, and carbon dioxide is produced. Here, hydrochloric acid, calcium sulfide, and carbon dioxide is produced as waste. This HCl generated, if it is released to the atmosphere, it can cause asthma and other respiratory problems to the people nearby. Calcium sulfide, which is another waste generated, is a foul smelling compound, and if it is dumped in soil, it can make the soil infertile. And we all know carbon dioxide has greenhouse effect. So because of the problems caused by the waste generated in this method of synthesis of sodium carbonate, another method, Solvay's process, came up. In Solvay's process, sodium carbonate is synthesized from sodium chloride and only calcium chloride is formed as the byproduct. So here we have tried to minimize the waste generated because waste can cause problems, it can affect the environment and the human health. In 1863, the British Parliament passed the first Alkali Act, and according to this act, not more than 5% of hydrochloric acid can be released into the atmosphere by a alkali plant. Now, let us see another a term called environmental factor or E factor. This term was given by Roger E. Sheldon, and it is defined as the ratio of kilogram of byproducts or waste to the kilogram of products. So here you see this example. We have taken two industries, one is oil refining and other is pharmaceuticals. Here we can see the production of in the oil refining and pharmaceutical companies in tons. Oil refining companies, their production is much larger than pharmaceutical companies. However, the E factor of oil refining companies is much less than pharmaceutical companies. This is because oil refining companies produce less waste compared to the product generated. So oil companies produce a lot less waste than pharmaceutical companies as percentage of material processed. So we can say lesser the value of E factor, better is the production. So here we should try to minimize the E factor of a reaction in industry. Now let us come to the second principle of green chemistry. This is about maximizing atom economy. This principle states that there should be maximum incorporation of the materials used in the process into the final product. Now, before we see what atom economy means, let us first see what is percentage yield. So, whenever there is a reaction, reactants are converted into product, and the amount of product formed, we quantitatively assess it using yield. So, yield is defined as actual yield of the product divided by theoretical yield into 100. If this value is high, we say it is a good method. So, traditionally, the efficiency of a reaction is measured by calculating percentage yield. But however, if a reaction has 100% yield and it is generating waste or byproduct, in terms of green chemistry, we cannot say it a green synthesis. So, yield totally ignores the use or generation of any undesired product that is an intrinsic part of any synthesis. Though the reaction has 100% yield, but if the waste or byproducts are generated, it cannot be a green method. For example, Grignard, Wittig, and Hoffman reactions have 100% yield, but they do not take into account the byproducts produced. So, in green chemistry, uses the term atom economy. In 1990, Barry Trost introduced the concept of synthetic efficiency, and which is he named as atom economy. So, atom economy refers to the concept of maximizing the use of raw materials so that the final product contains the maximum number of atoms from the reactant. So, atom economy is simply the formula weight of the desired products divided by the sum of the formula weight of the reactants. So, this is the formula. Atom economy equal to formula weight of atoms utilized divided by formula weight of all reactants into 100. So, uh, green chemistry, according to green chemistry, a synthesis is green and efficient if its atom economy is high. So the efficiency is calculated in terms of atom economy in green chemistry. Now let us see how to calculate atom economy of a reaction using that formula. So this is one example. You can see butanol is treated with sodium bromide and sulfuric acid to give butyl bromide. And let us calculate the atom economy of this process. These are the formula weight of the reactants and the product, desired product butyl bromide. So to calculate the atom economy, we will divide the 137 with the total sum of all the reactants 74, 103 and 98. So atom economy is 137 divided by the formula weight of reactants. So here we get the value 49.8%, the atom economy of this particular reaction. So now it is clear how we can calculate atom economy of a reaction if we know the formula weight of the reactant and the desired product. Now let us take another example. This is a Grignard reaction. Here this Grignard reagent phenyl magnesium bromide is reacting with an acid to form tertiary alcohol. The desired product has molecular weight 198 and the reactants has molecular weight 181 and 88. As 2 mole of Grignard reagents are reacting, so the molecular weight of the reactant will be twice of 181 and 88. So atom economy will be 198, the formula weight of the product divided by formula weight of the reactants, 2 into 181, which is 362 plus 88. So the atom economy of this particular reaction is 44%. So we can say, though in a Grignard reaction the yield is very high, but atom economy is less because of the byproducts or the waste generated. This is another example of synthesis of epoxide. So in this case, the desired product, epoxide, the molecular weight is 44, but the reactants ethylene, calcium hydroxide, and chlorine, their molecular weights are 28, 74, and 71. So when we calculate atom economy, the atom economy of this reaction is very, very low, that is 25%. So this is not a very atom efficient reaction, and in terms of principles of green chemistry, this is not a good method for synthesis of epoxide. Now, another example is the Wittig reaction. In Wittig reaction, this acetone is treated with Wittig reagent, and the product obtained is an alkene. Here we calculate the atom economy by dividing formula weight of the product alkene, which is 70, to the molecular weight of the reactant 58 and 290. So the atom economy of this reaction is very low, 20%, because you can see here that triphenyl phosphine oxide is generated as a waste, and so the atom economy of this reaction has reduced drastically. Now we will see what are atom economic reactions. Atom economic reactions have 100% atom economy. So there are certain reactions whose atom economy is 100%. For example, the rearrangement reactions, addition reaction, Diels-Alder reaction, and other concerted reaction. Now, what is a rearrangement reaction? Rearrangement reaction is a reorganization of the atoms that make up the molecule. Example, Claisen, Cope, Fries, Bachmann, and Pinacol rearrangement. So this is an example of rearrangement reaction where atom economy is 100%. So the atoms are getting rearranged. So the formula weight of the reactant and products are same. Therefore, the atom economy of rearrangement reactions is 100%. Now, what are addition reactions? Addition reactions involve addition of a reagent to an unsaturated group. Example, cycloaddition, bromination, or Michael addition reaction. This is an example of addition reaction where atom economy is 100%. So ethylene when treated with bromine give the 1,2-dibromoethane, the addition product. Another example is the hydration reaction. So both these reactions have 100% atom economy, as the formula weight of the product formed is equal to the formula weight of the sum of the formula weight of the both the reactants. Now, a third type of reactions which are 100% atom economic are the Diels-Alder reaction. It is a cycloaddition reaction between a diene and a dienophile. This is a Diels-Alder reaction between 1,3-butadiene and ethylene to give this cyclohexene. This reaction again has 100% atom economy because formula weight of the cyclohexene and formula weight of both the reactants is equal. So these types of reactions are called atom economic reaction, which have 100% atom economy. Now there are another type of reactions which are atom uneconomic reaction whose atom economy is not 100%. These are the substitution reaction, elimination reaction, Wittig reaction, and reaction with Grignard reagent. In a substitution reaction, one atom or group is replaced by another. The atom or group that is replaced is not utilized in the final product. Because the atom or group that is replaced is not utilized in the final product, so formula weight of the reactant and formula weight of the product will be different and atom economy will not be 100%. This is one example. Here, this alkyl halide when treated with sodium cyanide, bromide is getting replaced with cyanide. So this is a substitution reaction, and therefore the formula weight of the product is different and formula weight of both the reactants is different. Now another is the nitration reaction. Here hydrogen of benzene is getting substituted by nitro group. So both these type substitution reactions are atom uneconomic reactions. Now other type of atom uneconomic reactions are elimination reaction. Elimination reaction involve loss of two substituents from adjacent atoms. As a result, unsaturation is introduced. So this you can see an example. This is an alkyl halide. Here hydrogen and bromine is removed and an alkene is generated. So this is an elimination reaction when hydrogen and bromine are removed. Then this reaction is atom uneconomic because the desired product is this, and along with that KBr and water are the byproducts. So the molecular weight of the product is much less than the molecular weight of both the reagents together. Another example is the formation of alkyne from this alkene halide, and In presence of sodamide, this reaction is again an example of atom uneconomic reaction. Oxidation reactions are also atom uneconomic reaction. The another category of atom uneconomic reaction is wittig reaction. So in a wittig reaction, there is formation of phosphine oxide, because of which the reaction has a low atom economy. So you can see this example, wittig reaction, in which phosphine oxide is formed, and the atom economy of this reaction is only 20%, very, very low. Fourth type of atom uneconomic, which I have discussed here, is the reaction of with Grignard reagents. So when Grignard reagent is treated with this acetone, the product is formed, and atom economy of such reactions is less than 100%. So these are some examples of reactions whose atom economy is less than 100%. So these are atom uneconomic reactions. Now, when we are considering any reaction for their greenness, we should consider their atom economy individually, because at times catalyst can maybe require insignificant amount. The catalyst may be unrecoverable. In case of some atom uneconomic reactions, there may be elimination of water, and just elimination of water does not significantly detract them from the greenness. This reaction will still be said green, though the atom economy will be less, just because elimination of molecules like water is taking place. Now we will see another example where will calculate the atom economy. Here we are taking the example of ibuprofen. Ibrufen is developed as an analgesic by Boots Company in 1960s. Later on, a green process came up in 1991 by the BHC company. So this is the brown synthesis of ibrufen by Boots Company. You can see this compound 1 is acetylated in presence of aluminum chloride, and this acetyl derivative compound number 3 is synthesized. Compound number 3 on reaction with 4 and 5, the ethyl chloroacetate and sodium ethoxide, forms an epoxide. This epoxide, compound 6 on reaction on hydrolysis, forms aldehyde, compound 8. Aldehyde on reaction with hydroxylamine, compound 9, gives compound 10, an oxime. Oxime with loss of water gets converted into cyanide, compound number 11, and this on reaction with water gets hydrolyzed to carboxylic acid, compound number 13, which is ibrufen, and ibrufen has formula weight 206. So this is the synthesis of ibrufen, and here you can see there are 6 steps. Step 1, acetylation. Step 2, formation of epoxide. Step 3 is formation of the aldehyde. Step 4 is formation of oxime. Step 5, formation of cyanide, and then hydration. Step 6, to give the carboxylic acid, the desired ibrufen product. Now let us calculate the atom economy of this particular reaction. So if we'll see in this reaction, our desired product is ibrufen, compound number 13, whose molecular formula weight is 206. Now out of all these 13 reagents, the reagents which we will consider for atom economy are reagent 1, reagent 2, reagent 4, reagent 5, reagent 7, reagent 9, and reagent 12. So formula weight of all these will be summed up, and the formula weight of all the reagents is 514.5. So atom economy of this synthesis is formula weight of ibrufen 206 divided by formula weight of all reactants 514 into 100. So atom economy of this synthesis is only 40%. Now there are certain drawbacks of this brown synthesis, that is in most of the steps reagents are used rather than catalysts to carry out these transformation, because of which large amount of waste is generated. This is a 6-step process, a lengthy process, and the atom economy is 40%, which is very low. So these are certain drawbacks of this particular reaction, and this reaction is not a very green reaction because it is not fulfilling the first principle that we should prevent the formation of waste, and it is not fulfilling the second principle, that is maximization of atom utilized. So atomic economy is again low in this reaction. Now This is another method for synthesis in ibrufen, and this synthesis was given by BHC company, and this synthesis is considered to be a green synthesis of ibrufen. Here you can see ibrufen is synthesized in 3 steps: step 1, step 2, and step 3. In the first step, compound 1 is acetylated in presence of HF to give this acetyl derivative, which then reduced with ranitidine nickel and hydrogen to form the alcohol. This on carbonylation in presence of palladium as a catalyst give the ibrufen product. So here you can see HF, ranitidine nickel and palladium. 3 catalysts are used in these 3 steps. Now let us calculate the atom economy of this reaction. So the reagents which we will consider again for calculating the atom economy is reagent compound 1, compound 2, this 4 hydrogen and 6 carbon monoxide. So total formula weight of all the considered reagents is 266. Atom economy is formula weight of ibrufen 206 divided by formula weight of reactants 266 into 100, 77%. So this reaction has a greater atom economy than the previous reaction, which is only 40%. Now, so let us see the features of this reaction. This synthesis of ibrufen by BHC company is a 3-step process. All the 3 steps are catalyst. In the first step, HF is used as a catalyst. Second step, ranitidine nickel is used as a catalyst. Third step, palladium is used as a catalyst. Now, in place of only catalytic amount of HF is used in place of stoichiometric amount of aluminium chloride for carrying out acylation, as in the previous method by Booth's company, where aluminium chloride was used for carrying out acetylation. Now here HF is used, so less waste is generated, but using HF has some safety issues. This reaction has 77% atom economy, so it has high atom economy. So that's why we are considering the BHC company method of synthesis of ibrufen to be greener as compared to the Booth's method of synthesis of ibrufen. The Booth's method is a 6-step process. Here stoichiometric amount of reagents are used, not catalytic amount. Atom economy is low and a large amount of waste is generated. So, and it has only 40% atom economy. So the better and greener method is the green synthesis of ibrufen by BHC company. So this particular synthesis is obeying the principles of green chemistry. It follows the first principle of green chemistry, which states prevent waste. It is following the second principle of green chemistry, that is maximize atom economy. This principle also follows the principle 9 of green chemistry is being followed by this method, that is the use of catalyst, not stoichiometric reagents. Now here we have seen how to calculate the atom economy of a multi-step synthesis, and based on atom economy and other factors, how can we consider a reaction to be green or not? Some questions based on first and second principle of green chemistry are, that is, how is atom economy different from yield? Another question on this topic is, what is E factor? Next question is, give example of substitution nucleophilic unimolecular and substitution nucleophilic bimolecular reaction and calculate their atom economy. Another question from this topic is, rearrangement reactions are 100% atom economic, explained with example. Next question, a reaction uses stoichiometric amount of reagent versus one that uses a catalytic amount of the same reagent, comment using example. Next question is, in terms of principles of green chemistry, compare the traditional and green synthesis of ibrufen. Last question is, in addition to atom economy, what other aspects of synthesis need to be considered before one calls the synthesis green? So these are some of the questions which can be framed from first and the second principle of green chemistry. Here are certain books which can be referred for these topics. The first book is Green Chemistry, an introductory text by Mike Lancaster, and in the book is Green Chemistry Theory and Practice by Paul Anastas and John C. Werner. And next book is an introductory text on green chemistry for undergraduate students by Dr. Indu Takar Sidwani and Dr. Rakesh Kumar Sharma. With this, I will end this video. In our upcoming videos, I will discuss about other principles of green chemistry, principle 3 to principle 12 of green chemistry. So please like, subscribe, and wait for our upcoming videos. Thank you.